Okay, well, good afternoon. Welcome. We've got the second exam review. It has a reputation of being more difficult than the first one, but not as difficult as the third one. Just keeps building as we go through. At first, of course, everything from the past exam is still could be used on this exam. So this is one thing that makes the physics kind of difficult. It just keeps building. So let's get to building. We're primarily introducing Newton's laws, really, where we're taking off from what we did in the first section was kinematics, and we talked about, velocities, accelerations. Now we get into what's responsible for that, and that's really kind of where we're really starting more with the physics now. What gets things to accelerate? Well, we know that it's got to be forces. And Newton has these three laws. We primarily use the second one, but real important are this first law is that an object at rest tends to stay at rest unless a net force, usually we say unless a force acts on it. It's really a net force because you can have a zero force and it doesn't mean that there's no forces acting. It's just that when we add them up, they add up to zero. If there's no net force, then the acceleration will be zero or the velocity would be constant. It could be constantly zero or it could be some constant for this thing maybe traveling through space. Could have some constant velocity. It just keeps going forever. That's the idea. So I think most people have this idea pretty well in mind. Newton's second law really kind of comes in two parts. The idea that we have the good old F equals ma, it really is the net force that is the F. If we have more than one force, we need to do the vector sum of these, and that forms the net force. So there's really these kind of two parts that we have to figure out what is the net force due to all the forces acting on this object. We add them up vectorially, and we come up with the net force. Once we have the net force, then that allows us to speak about what happens to the acceleration. Usually we write F equals ma, and that becomes kind of the mantra for the whole course. But probably in terms of concept, think of it in terms of the acceleration is going to be directly proportional to that net force. It's going to be in the same direction. It's a vector, just the force vector and the acceleration vector are in the same direction. Mass is just a scalar. So the acceleration is directly proportional to the net force, in the same direction as the net force, and inversely proportional to the mass. And so hopefully you've got all this. But it helps to kind of break problems down into kind of two parts with the second law. First, do the net force by summing up all the forces, and then we can apply that net force to F equals ma. A lot of students tend to want to call this a force. Really what we want to do is line up all our forces, put them all on one side of the equation, and then the other side of the equation will be equal to ma, or the acceleration. I'll specify this more. Now, as far as adding up these forces, I think it's best to draw the forces coming as they act on an object. In this object, we've got a couple forces here. Newton said, and I think it's intuitively rather obvious, that net force, we would take this force, we could add it to the other one. In the past, we have added vectors head to tail, head to tail. If I've got the first force, I can take this second force and put it over here. So I'm going from from tail to head, and that would be the net force for those two things. So that's the basic idea we're going to be playing with. Okay, and then there's also Newton's third law. Action-reaction is this idea that if you have two things that are having a force between them, all forces come in pairs. All forces come from other objects. They don't just come out of nowhere. Although there can be things like a force field that's due to some object, like the gravitational field, and we'll get into later the electric field next fall. But the idea that if we have these two skaters and they're here and they push off one another, it really doesn't matter who's doing the pushing, who's bigger than the other. The force on one is equal and opposite the other one. So one could be pushing and the other one just holding their arms, or they could both be pushing. Regardless, there's this action and reaction, and it's taking place between the objects. So we'll be looking at these. Let's start to look at some of the forces that we have. The first one is gravity, and that's probably the most elusive thing. We're not really answering what is gravity, but we know some things about it. Your very first lab, you did a free fall experiment where you dropped the bob and you got the acceleration. One thing you got the 9.8, or hopefully close to 9.8. But that is a constant acceleration. It applies when the object first starts to move and also after it's been falling for a while. So it's independent really of its motion. The idea is there's going to be this force of gravity, and we want to say that F equals ma. So we say the net force, well, there's just one here, that's that force of gravity. That net force has to equal the mass times the acceleration. We know from what we did in the lab that acceleration has to be g, and that was 9.8. And so that force, I'm assuming that force we see is in the downward direction. And this is what we call the weight of the object. So the F sub g, or the weight, will be equal to mg, and that's why we're using this all the time. I'm sure you've seen that a lot. Hopefully you're using it a lot. If we want to hold this thing in equilibrium, we can add another force, and that's something like the tension in the cord or the string that's maybe holding this mass. And in this case, it's going to be held in equilibrium. That means the net force, we've got two of them. I'm calling up positive, so that's T minus mg, the gravity coming down. That net force should be equal to ma. It's not moving, so the acceleration has to be 0. That's equal to 0. And so we can solve then for the tension. That's just equal to the weight of this thing. All of this is kind of common sense, but what can be helpful is starting to see how we're starting to think like Newton as far as breaking a problem down. We want to keep these steps very clear, where we take two forces, we get their net force, and then we set that equal to net force equal to ma. Things can get subtle. How about another thing of equilibrium? Let's say a person wants to just stand on something like a bathroom scale. Gravity pulls down with mg. What other forces are acting? Other forces that are touching him? The normal force is pushing up. And beyond that, there's no other forces, no other things that are touching this person other than through the soles of their feet. Action and reaction, the force on the scale is downward. The action force on the person is upward, the force on the scale is downward. And that would be indicative of what the scale would read, and that would be the weight of that. So the normal force is equal to the weight. Of course, now this is kind of common sense that the scale should read the weight of the person. Again, we'll look at the net force is the normal force up minus mg, and now we can take that net force and set it equal to ma. It's not moving, so the acceleration is 0, that's 0, and we can solve for the normal force, and it's equal to the weight. So all of this should be just real common sense. Now things can get a little stranger when we have an accelerated, let's say an elevator car. And let's say you have a person inside that car, and we put in something like a bathroom scale and they stand on it. Now if this car starts to accelerate upward and this person is standing here, we can look at this as the net force on this thing. Then the normal force is the scale pushing up. So again, it's very similar to what we did over here, only the magnitudes you'll see will be a little different. Normal force is up, minus mg down, and the net force should also equal ma, so we can take these two ideas and put them together. depending on what the acceleration is, the normal force, when we solve for that, I've got ma, I'll take mg over to the other side, so we end up just adding them, mg plus a. So the normal force, if you're accelerating upward, is going to be more than just the normal force was here when you're just standing on the scale. That normal force is what we call the apparent weight of the person. The actual weight, gravity is still pulling with mg, but you will feel heavier. If you've ever been in an accelerated elevator car, you feel heavier, and that normal force will show that. The scale is going to read more than just mg, your weight. It's going to also add in ma, whatever your acceleration is.
Question.
Yeah.
So this is in reference to the scale, not the person or the actual elevator, right? Because they'd each have their own normal force, right?
Okay, there can be lots of other forces happening.
They each have a normal force, right?
Okay, right. And when we do problems, typically we focus on a particular piece. In this case, I'm looking at the forces acting on the person. Now, it's true that upward force then will equal the reaction force on the scale. And since that normal force is more than the weight, that force on the scale is more and is going to read higher. You're not imagining anything. But again, we say the force due to gravity is mg. Now, there's lots of other forces. There had to be forces on the elevator car pushing up. So we could play the whole game with that. We probably would need to know things like, well, what is the mass of the elevator car? So as far as breaking problems down, knowing just where to focus is going to be important. So here I'm just focusing on this person. There's, again, just two forces. They always come from other objects outside that body or here. mg pulls. Of course, it pulls a little up on the earth, which isn't readily apparent. But certainly things that physically touch, or at least in the classical sense, like the person standing on this, there's this force on the person that's up. Okay? I'll emphasize this as we go and get into more difficult cases. How about another one that's in equilibrium? We've got a couple chords, and we're going to hang some mass to it, so it's got some weight to this thing. And maybe the question is, what is the tension in these two chords? Of course, I haven't specified anything. This drawing is such that that's 60 degrees and that's 30 degrees. So if you want to use some numbers, I want to just kind of look at how we set these things up and kind of look at the algebra as kind of making sense, hopefully making sense of what's happening in the problem. Now, one thing, tension, we're introducing this kind of a new force here, is if you think of a chord, we'll often talk about the tension in the chord. And usually we'll just give it a magnitude because it does have a direction, but it depends which end we're talking about. If I want some tension in the chord, is it that way? Or is it that way? Or what direction is it? This end of it, as I pull away from it, the chord wants to pull back on my hand, so the force of the chord on my hand is in this direction, even though I'm pulling in this direction. So this is kind of this action-reaction stuff. The other end of the chord, I'm pulling it this way. The chord wants to pull it back in this direction, action and reaction. So knowing where to focus is important. Now, I could have put the tension up here. The tension of this chord pulls. I'm going to really actually be focused on the knot here. That's going to be the object that I'm going to look at. We've got all these other objects here, like the ceiling. I don't know. I assumed it's not going to fall. And I attach this cord to it. I expect this tension in this direction is pulling that way. This is going to be pulling on the ceiling this way. Whatever tension is pulling this way, this is going to pull back here. And we could break it down, even a section in here. We could look at the cord that's in there and what the tension is. So what we'll do is we'll just call them, like T1 would be the tension in this one. T2 is the tension in this one. We are going to solve primarily for the magnitude. Now what I'm going to call into equilibrium. There's lots of things here that are in equilibrium. I could have focused here, and it probably would be a good idea to also kind of first focus here. There's going to be an mg here, and there'll be a tension here wanting to hold it there. It's kind of obvious this tension is going to equal that weight. And then that tension gets applied in the downward direction up here, and that downward force is going to be mg because of the gravity on this thing. So now I would maybe need to find these two tensions. The idea that it's in equilibrium, so that means the acceleration is 0 and the net force has to be 0. What can be really helpful is to break things up into an x and a y coordinates, and so we can look at the sum of the forces have to be 0 in both the x and in the y direction, and so we can look at the components of the force. And again, I'm focusing on a little knot here where these things are tied together. The x components, I need to break up this tension. I've kind of got the components in here already, and so it's a little deceptive to look at this, but essentially this is coming up here. We've got a force or tension in this direction. I want to break it into a couple components. One thing you want to see is this angle should be equal to this angle. Hopefully your geometry is good enough. The idea that these two lines are parallel and that they're cut with a line. This angle will be that angle. This angle will be that angle. So it allows me to kind of focus in on this section here. And I can get these components. X components would be T2, would be in this direction. In the x direction, I would do it times the cosine of theta 2. Hopefully you've got your basic trig down here. So I've got that. That's going to be in the positive x direction, so that goes in as a plus. I'm back in this direction. I can get the magnitude of this component. I take T1 times the cosine of theta 1, and that's going to be back in the negative direction. So I first do it as kind of magnitude here to get that, and then I realize that that force is in the negative direction. And that has to be 0. Same is true for the y components. In the y direction, I can get T1 times, now I'll use times the sine of theta 1. This component will be T1 times the sine of theta 1 would be that component. This component is T2 times the sine of theta 2. So they are both in the upward direction, so they both go in as positive. Gravity is pulling down, that's minus mg. Now we can tie these two things together. The x components and the y components both have to be 0. From the x components, I could solve for either T1 or T2. Essentially, consider that these two tensions are what we would be looking for. And I realize that all these symbols, students tend not to like this. They want to know what it is. If you want to fill in some angles, you could say, well, that's 60, that's 30, and stick in. And so you got the sine of those angles. You know what they are. But the question might be, what is T1? What is T2? If I do know those angles. So from the x component, I solve for either T1 or T2. I've got T2 here. I'll substitute it in. It comes in, and it's really now just kind of algebra, the way this works. If you want to do sine theta 2 over cosine theta 2, that's going to be the tangent. You can kind of see how we've got this. I factored out the T1 because I would typically want to solve for what is that tension in that chord. That tension would be mg. Well, you can read it here. It's not a trivial expression, but this would be the result of that. I would just go ahead and stick in the numbers in my calculator. I'd pull it up and I'd get T1. Once I have that, now I could go back into either this equation or this one. I've got, this one is kind of the simplest one. If I want to get T2, once I have T1, I can stick that in, or stick it in here. And then I can, and if I know these angles, then I can get T2. And
you define the knot as 0 on like an XY grid, and that's why cosine T2 is is positive and T1 is negative?
Right. What you should do, okay, there's lots of ways of handling this, but the clearest way is to get a real accurate drawing. Okay, you put in a coordinate system what you want, and usually we'll call this the X and the Y, kind of like standard. And in the standard configuration, we call this the plus X and that the plus Y. So as long as those vectors are in that direction, they would follow that sign convention. So that's why, like with tensions, I want to talk about the magnitude of the tension, and then look at, am I applying that tension here, down in the knot, or am I applying it up here? They're in opposite directions. So I do want a clear, what we call free body diagram of that to see which way those vectors point. Okay, so these are similar to homework type problems, but I'm just kind of using these as examples to illustrate some of the forces that we're going to be dealing with. Another one is friction. We've got kind of two types, static friction and kinetic friction. Static friction is where the surfaces are maybe rubbing a little bit, but they're not sliding or slipping on one another. The idea of that is if you took a kind of a microscopic level down here and looked at this, these little craggly pieces of stuff are going to be cut into one another. And if we try to push the object against those, they push back, action and reaction. So the idea is if I apply a force on this thing in this direction, it will dig in and want to pull back with exactly the same force back in the other direction. And so if there's no force there, F equals to 0, there's no frictional force. The more I tend to apply a force to this thing, wanting to pull harder and harder, this thing will just continue to pull back. And so the static friction is just equal to that force all the way up till at some point it's going to break down. If you think about this model again where they're digging in, they dig in, they push back until some level where they slip, and then the thing breaks down. There will be a little bit of a complicated thing where we're going to kind of gloss this part over. But once it gets moving, these things are just rubbing on one another. And this is a simplified look, by the way, of friction. This is only approximate. It's a good model for us beginning to play with this. But the idea that kinetic friction would be some constant times the normal force. This normal force is the force between the objects. It's telling us how tightly these surfaces are pushed together. The more tightly they're pushed together, the more these things tend to dig in and make it difficult to move. Static friction, much the same way, other than, it always doesn't allow anything to slip up onto its maximum value. And a lot of problems we're dealing with, we deal with static friction. Usually it's less than or equal to mu sub s times the normal force, but very often we want to get the maximum force. It's right at the verge of slipping, and we'll look at some cases like that. And then we can just use this as an equality. It will be a little easier to deal with that in problems. Okay, so hopefully you've done that. Okay.
For static friction and kinetic friction, the way we use them are the same, just that we plug in the normal force over, but one just has a lower value than.
Right, generally, yeah, good point. Usually the kinetic friction, this mu sub k is less than mu sub s. Okay, and let's see. Also, these are really kind of approximate. Friction is a more complicated thing than that. And we know, as we'll get into some Chapter 6 problems, that there's things like air resistance, that kind of stuff, where it's not so simple as this. And we'll look at some of those. But for the most part, we'll be playing with these two ideas. And your point is good and well taken, that mu sub s is usually greater than mu sub k, and there is this kind of transition where it just starts to slip. Once it starts to slip, it just stays a constant force as we drag this thing across the floor. Okay. Okay, let's get into a problem here. Let's say we've just got an inclined plane, and I'm going to put, I don't know what this, I guess that's not going to quite put it like that, with some block on top of it. And let's say for right now it's being held, it's in equilibrium, it's not slipping. We'd be dealing with static friction because this thing hasn't moved yet. I'll look in a little bit. What we're going to lead up to is that we can take something and put a block on there, and we could lift it and lift it and lift it until it finally slips. And that would be that kind of breakdown point. So I want to lead up to that, but let's first deal with this where it's being held in equilibrium. Okay, now hopefully you're getting your force vectors down. When I place it here, I'm on this problem. I'm taking my x-axis and I'm going to put it along the surface, y-axis like this. And the idea is that this thing is going to start to move, it's going to start to slide. And there's an advantage to me doing my x and y axes like this, is that I've got all of the motion in the x direction, but in the y direction, assuming we don't break through here, as long as this holds here, we're going to have no motion in the y direction at all, strictly in the x direction. So in terms of equilibrium, when we add up our forces, it's going to be equal to 0 in the y, because it's not going to go up or down. But then when we do the sum of the forces in the x direction, well, it's going to be 0 here, but in a little bit we'll look at how it can move in that direction. So what we'll do, we need to deal with all the forces that are acting on this. Of course, gravity is pulling down. The force of this surface is usually broken immediately up into two components. One is the normal force pushing out, so that this block, instead of falling, is being held up. Also, if there's friction, that friction is along the motion of this thing, because if it slides, it's going to be applied along that x-axis. So these are the three forces that are acting. We do the sum of the forces in the y. That's going to be a normal force. That's in the plus direction, so that's that way. We've got to get a minus mg cosine theta is going to be the component of gravity along the y-axis. And hopefully you're doing well with that. Getting these angles can be a little tricky. Where this thing is sitting, this is, the way this is drawn, this is 30 degrees. There's going to be another angle. In fact, you could, a number of ways we could do this. If this is 30 degrees, this is going to be 60 degrees. And if that is 60 degrees, this is back to 30 degrees. Getting these angles, it's important that maybe that you do a real accurate diagram of this. It can be really helpful to maybe get one of these, or just a ruler and a piece of paper, and carefully lay this thing out. It's easy to mess up your angles. You know, if this is theta, how did I know that was theta? You want to be clear that you can get those angles. Lots of ways of looking at that. It's important now, when you get in an exam, there's a tendency you see a slope and you draw it, and most people will immediately draw, and they invariably draw a ramp that looks like this. It's 45 degrees. Now the problem with that is you can mess up your angles if they aren't exactly 45 degrees. You're trying to keep track of them. Everything's looking like it's at a 45 degree angle. And so again, be careful. Try to exaggerate your angles a little bit. If he gives you a drawing that almost looks like 45 and tells you that there's some other angles in here, lay it out and draw maybe the small angle here and the bigger angle on the other side, and keep the geometry straight. And if you draw this carefully when you're studying, it will help you retain what's happening here. Kind of etch it into your mind and see what you're doing. So if you're having trouble with that, I would encourage you to do that. So I did have, this is that angle theta. So if I want to get the y component, this is going to be mg, and I take it times the cosine of theta. This is where we're different than like a math class. Typically in a math class, you make this your x-axis, and you've got some angle, and let's see, I forgot what I was going to say. We say that the sine of the angle is the side opposite the angle. The cosine is the side adjacent. What gets tricky here is we start to flip these triangles around. And I'm going to put this here, and I want to break my components. Now, the best way to keep things straight, people can mess up. They'll look at this and they'll say, well, oh, wait a minute, I'll do a smaller one. They'll look at this and they want to put this here, and they want to make the hypotenuse of this thing the component. Now, what you want to be careful of is that you want to get your axes, and then it helps to draw kind of a rectangular box around mg to get those components. And when I put those in, those components here, they should add up to mg. The right angle is here going over to here, so that this one is less than mg itself, and this one is less than mg. The test is always these components have to add up to this vector, and so see if they do that. And this is kind of a rectangular parallelogram, and they come and give me that. So this is again is going to be the normal force is straight up. This component here is going to be minus mg cosine theta. I could go ahead and solve for the normal force. I may need that if I'm going to do friction. And then I can look in the x direction. We've got the frictional force is back in this direction. We've got a component of gravity pulling down. This is going to be the same as this side, which is going to be mg times the sine of theta would be that side, or that would be that component. So again, you need to be able to break these things up, and they can get a little tricky as we flip these triangles around. So in the x direction, that's force minus mg sine theta. That has to be 0. So this whole thing is still in equilibrium. Okay, now let's come back to this idea that I was suggesting. Let's say, let me get a little rougher surface here. I've got a block on here. And if I lift it up, it doesn't move, it doesn't move, it doesn't move. And as it goes to a certain level, I think, okay, it starts to move. It all depends on the coefficient of kinetic friction here, or static friction, excuse me. The idea that if we take a look at this and we increase this angle, what's going to happen to the normal force? Well, the normal force was equal to mg times the cosine of theta. So as we get bigger and bigger, theta gets bigger. The normal force is going to get less and less and less. So those two surfaces are not being pushed together really, hard, but as they go up, it gets weaker and weaker, and then the thing can finally slip. So right at the point where it slipped, if we accurately measured that angle, we can say that, well, the static friction is always less than or equal to mu sub s times n, except when it's right at its maximum. So the idea, we're up at some angle just before that thing slipped, it should be just equal to mu sub s times n. So if I take this normal force and I go ahead and put it in here for n, and mg was what I had here, these mg's cancel, and then the sine over the cosine is the tangent, and so we can get mu sub s, the coefficient of static friction, by getting the angle where it just lets go. So that's kind of a fun little idea. These coefficients, they're just dimensionless numbers. There's no units associated with that, so you might get like a 0.2 or a 0.4, something that he would typically give you in the problem. Okay, here's kind of the first problem on the practice problems. You've had a chance to look at these. The idea, let's just kind of look at the problem as it's been stated. We have a 7 kilogram block and we're pushed with a 35 Newton force. Now look at that 35 Newton force. We're not just pushing it in the x direction, we're also pushing down on it. It's going to have some components in the downward direction. Okay, what else does he tell us? Okay, it's 30 degrees below the horizontal is the direction it's being pushed. The surface has a coefficient of friction of 0.25. Okay, it says, what is the acceleration of the box? Now, you might say, well, is that the coefficient of static friction or kinetic friction? And that would be okay for you if you wanted to go talk to him. But the thing isn't certainly going to accelerate. If the thing does accelerate, that means those surfaces have to be slipping. And so indirectly, maybe he's trying to sense and see if you know that, hey, that would be the coefficient of kinetic friction. Kinetic frictions are a little easier to solve. But let's look at all the forces that are acting on this. We've got this force coming in, this 35 Newton force. We've also got gravity here. The tabletop is pushing up. And then also, as this thing is going to move or start to accelerate, we're going to have this frictional force back in this direction. So those should be our forces. I do expect that this is sort of going to win out, and I do expect it to accelerate this way, but don't confuse that with these forces. These are the only forces that are present. Now it's we're gonna look at the forces in the y. In the y direction, this thing I don't expect to jump up or crash through the tabletop. It should stay. Those forces should be zero. There should be zero acceleration, and therefore the forces should be zero. So in the y direction, we say the normal force minus 7 kilograms g minus, we do the 35 times the sine of 30 degrees. Sine would be opposite that. That would be the component that's down. That should be equal to 0. And we can solve for the normal force. Just take this other stuff over to the other side. And I see a normal force of, do the math, it comes out 86.1 newtons is that upward force. Notice that it's not just mg. M would be the 7 kilograms times g. This is the weight of the object. But it has the weight of the object pushing down, but it also is being pushed down by this 35 Newton force. So this increases the normal force, and it's the normal force we want to focus on, not just the weight of this thing. That tells us how tightly these surfaces are pushed together. Then we can do the forces in the x direction. I don't expect that to be 0. I expect it equal ma. There's going to be some acceleration taking place. So I've got this 35 Newton times the cosine 30, but the frictional force is in the negative direction. So again, this 35 is in the plus direction. This is in the negative direction. And then now for the friction we can put in, it's going to be 0.25 times the normal force. And from this one I can bring that normal force, well, I guess I got it here. The friction is mu sub, be mu sub k times the normal force. We'd bring that normal force in and 0.25, and we can take that and put that in, again minus, and then do the algebra and we can get the acceleration of the block. So, okay, hopefully you're not intimidated by these kinds of problems. So, okay, let's get to something a little more complicated. Let's start to build this here. I don't have I've got a picture here, and I want to just kind of do this as kind of an example problem. I don't have exact numbers here. If you want to deal with some numbers, you can say, well, this is 30 degrees, 60 degrees. There's going to be some mass to this thing, and we want to get what the acceleration of this thing is going to be. That could be sort of the question. I've got a mass here, it's pulling down on this, and that is going to in turn pull this thing up. And the whole thing is going to move. And this is a case where we've got a couple of bodies that are interacting. They're tied together through this cord here that is going to have some kind of a tension in it. These things, right now at this point in the course, we're calling these massless, frictionless pulleys, meaning that all they do is change the direction of the force. So the upward tension here would pull down on this side of the pulley, would pull in this direction here, and pull on this direction up in the block. These two tensions at this point in the course are going to be the same as long as this is a massless, frictionless pulley. All it does is change the direction of this force from upward along the coast here, along the incline. Okay, so I've got two bodies, and I've in a sense got two free body diagrams. Sometimes it's helpful to draw them as a separate picture. If they're fairly simple, what I did is I did the free body diagrams in red here so you can sort of see them in context. And these forces on this one are kind of on this side. So I've got these two bodies, and this one is going to go up the incline. Ooh, or maybe it could go down the incline. Right now I've got a frictionless surface. I'm not including friction, although it wouldn't be hard to include it. I'm not sure exactly which way this thing is going to move. If this thing is heavy enough, it would pull it down the incline and pull this one up. If this one is heavier than this, it should pull the thing down and this one goes up. So either way it could go. And sometimes we can't tell what's happening. But the math can tell you. The physics can tell you. So let's do this. Now, when we have bodies that are tied together, it's helpful to have them move together. The thing that, of course, this cord is what's literally tying them together. That will have the same tension. But consider the motion. If I call one direction positive and implying that the other direction is negative. For instance, this one. I've got my x-axis for this one kind of laying along that incline. And oh yeah, I was going to lose my track here. Going up, I'm going to call this the plus direction. Sort of makes sense with the x-axis. But now this one, where usually we'd say, oh, force is in the y, we'll call up positive. What I want to do is I want to match these two directions and assign a direction. So I'm going to, for my math, I'm going to call this positive, moving this way. That implies that this one is going down, and that would be positive. This is going to be very important for watching your signs. You don't have to do it this way, but I think it's the clearest way to stay out of trouble. So I'm sort of assuming the thing is going up and this is going down. And I will solve for the acceleration. And if the acceleration is positive, then it is in fact, hey, it is going up. If I happen to solve for the acceleration and it's going in the down, or turns out to be negative, it's just going the other direction. So the math isn't kind of intimidated by me second guessing here what the direction will be. Again, I may not know what it is. So for this sign convention, for the upward one, calling that positive, we'll do the sum of the forces. That's going to be we've got the tension pulling up, minus this component of the gravity, that was down, times the sine of theta is going to be the same as that component, and that will be pointed in the negative x direction. Those are the only two forces acting in the x direction, and that should equal the mass of this block times its acceleration. F equals ma. Net force is equal to mass times acceleration. And if I want to solve for that tension, I could go ahead and do that. I'll need that in a minute. But let's turn about this one. Okay, I want to do the net force is equal to MA for this one. Again, I'm calling down positive. So in this direction, that's M2G, so that's going to go in as a plus. The tension is pulling back with a minus, and then that's going to be equal to M2 times the acceleration. Again, when the two things are tied together, it's imperative that we get the signs to work out. Because I'm going to be taking this tension and I'm going to substitute it in on this side, tying these things two together. So we've got to have this sense that we have a clear sense of what we'll call positive motion and what we'll call negative motion. So I can go ahead and take from this, these both have to be true, they're tied together. The tensions will be related as well as the accelerations. This is going to accelerate upward, this one's going to accelerate downward with some A. Okay, so I go ahead and plug that in for the tension, and it just follows down here. You can look at the math, and then I'm going to solve for the acceleration. Little messy, but I think you can see that these are just related to their individual masses and this angle that I've got, and I can solve for the acceleration. Now, as far as that sign of this, if this is positive, that just means that M2 is greater than this M1 sine theta. And so as long as that's the case, A is positive. If M2 is lighter and M1 sine theta is greater than M2, this minus sign will automatically give us a negative acceleration, and that just means it's going to be going the other direction. Okay. A little thing here, I said we could have done this, some of the forces in the y direction, and this is true, the normal force and minus m1g cosine theta has got to be 0, so you can get the normal force. I didn't include friction here. If I did, it wouldn't be a big deal. If it was going to go this way, the frictional force would be down here, and I would need that normal force times mu sub k to get that frictional force. So we need this if we have friction also included. But so while this is true, all I really need are just these two: the x term for this and the, I call it plus x downward for this one.
Is your kinetic friction like constant? So like for example, if we did have friction on that ramp, and we were going at some speed, like a high speed, would the friction be the same as if we entered it at a low speed?
Okay, for the kinetic friction we're dealing with, it doesn't matter what the speed is. Now you're touching on something that's more realistic. That sometimes that is a factor, like you got oils, and it gets to be a complicated whole thing. So our simplistic idea, and it turns out it's not too far off for most things, but certainly objects. Yeah, John.
When you're approaching the problem, do you know of a strategy to decide whether or not it's best to solve for t up the slope or down the vertical? I noticed here you did it up the slope, but it'd be more advantageous to solve for t.
Oh, okay, yeah, I did not solve for t. Now we got the acceleration.
Yeah.
So we could go back into either equation and get t.
Yeah, but I'm saying initially, here you solve for t going up the slope.
It would be always.
It's always better that way?
No, the tension would be going up.
Yeah, but I'm saying here, on the vertical, it's also pulling up.
Right, we've got these two, okay, yeah.
No, I know, I'm saying just getting an equation would be best.
Yeah, this idea that, tension, what direction is the tension? It depends what we're looking at. Of course, here with this tension, we're pulling that way on this one and pulling up. Now, what they would have is the same magnitude. And so when I'm doing this, I have this. This is strictly, there's no vector associated with this. These, I just stick in the numbers and I come up with a number here, and this, as well as if A is positive, this would overall be positive. It's possible when I solve this. A is negative, but this is still just the magnitude of t. The direction of it, I did have the assumption here with the sign convention, this going up. So this is plus t. I am assigning its direction this way, and I would assign this direction that way. But again, they have the same magnitude, so I can take this magnitude and put it into there. And these signs are really due to the direction of that.
I guess it's better to solve for t where t is in the positive direction. Because if you did it on the y side, you start out with negative
Oh,
is equal to blah, blah, blah.
okay, but certainly you could do that, but you could just move that over there and that over there. So, I see, yeah, so I mean, oh yeah, okay, I see your question. So basically, yeah, we could have taken this and solved for t here and substituted it in here. Absolutely, yes, yes. There's no one way to do it, yeah.
How about if mass one was connected to is that a pulley?
Yeah, this is a pulley up here.
Yeah, if there were two strings and then the tension connecting the pulley with mass 2 was only one.
Oh, okay, good. I've got some on that. So hang on to that a little bit. There's a more complicated one, but I've got 2 or 3 that illustrate that idea. So, yeah.
This question might be kind of similar to a previous question, but for solving for the first part, you do t minus, like the force down, and the other one you do m2g minus t. Does it matter which one has like minus t or t minus whatever? Can you just switch them?
Okay, a lot of ways you could do this, but the clearest way is to assign a direction. Now I assign this the plus direction, and this, that would imply if this is going up, this has to go down. So that implies this is positive going down. Now I could have assigned it the other direction. I could have said, well, this thing's going to slide, and I'll call this plus, and that implies that this goes up with plus. So your algebra is going to be the same. That sign would reflect itself down here in the negative. But either way you do that, you should have a clear answer what the acceleration is. Okay? Okay, and yeah, we've got some more complicated ones than this, but these are kind of good to get started with. In fact, let's jump into one here. This is this number 10. We've got a 10 kilogram blocks. We've also got some friction here. We've got a 5 kilogram block. This is tied through a cable over to the wall. And we've got a 100 Newton force. We're pulling at 10 degrees. We're going to pull this bottom block out from under this one. They're going to be sliding on one another, and there's going to be friction along this surface. There's also going to be friction along this surface, and so this a little more complicated. So let's kind of look at this. The 5 kilogram block sits on top of a 10 kilogram block. A cable is tied to the 5 kilogram block so that it cannot move. Okay, so it's not going to snap free. And 100 Newton force at 10 degrees above the horizontal is applied to the 10 kilogram block. The coefficients of friction for each surface are 0.2. Okay, and then he wants to know what is the tension in the cable and what is the acceleration of the 10 kilogram block. So we are going to move this thing out and get this thing to move. Okay, so got some added complications. So when we start this thing off, we're going to want to do a free body diagram, or a couple of them, to help separate this. I would prefer not to try to draw it all on top of this thing, but actually start to separate these two things out. This is going to be the top block. This is going to be the bottom block. And let's look at this top block. We've got the x-axis, we've got the y-axis, and I didn't write that down, but I'm assuming that then I'll call the x-axis plus x is that way, plus y is up. So for the top block, let's look at those forces. We've got an upward force of tension times the sine of, I changed that to 20 degrees. Now let me back up here, this confused some people on Friday. He gives you this as 70 degrees, I kind of want to draw those tension acting back here, so I guess I'd like to get these angled. And so if this is horizontal, this is 70, that's 90, this should be 20 here. And so when I draw that, I have this 20 degrees. If you wanted to use that 70, that would be, if you, along your y-axis, this angle here would be 70 degrees. You can use that if you'd like, but I think it was just easier for me to look at that as 20. So in the upward direction, or in the y direction, this goes in as a positive, it's going up. Always, from your free body, look at the direction of these forces, and they go in algebraically, like in that same form. I've got M1G is pulling down, or in the negative direction with the negative. I've got the normal force. This surface is going to push up on this block. That's N1. And I expect that the thing not to move up or down, so that the acceleration is going to be 0. And I can solve for the normal force N1. Just take these two to the other side. I'm going to need that normal force, because that normal force between the top and the bottom block is that pressure between the two. It's not simply, that normal force is not simply the weight that's hanging on it, but also the fact that the tension, this is a minus. In a sense, it's lifting up a little bit, and it's relieving some of the strain on that N1. So all the math is all taking this into account, that this is going to be less than the weight, because we're pulling up on it. Some of the forces in the x direction, we're going to have is going to be a frictional force, because as we pull this bottom block out, it wants to pull this one along. So hopefully the direction here makes some sense to you. There's going to be the bottom block, as it moves, is wanting to pull this one in the plus direction. Action, reaction, when we get to the bottom block, these are going to be in opposite directions. Again, when we pull that block out, it wants to pull this one in this direction, and this one wants to pull back or hold back on the motion of this as it comes this way.
The top block, the F1, is a friction, or is it a force?
Okay, it is a force and it is friction. So it's both.
Because the tension is, our motion to the top block is going to the left.
Oh,
So the friction force is...
okay, this block isn't going to move. It's being held in place. Let me go back. The original picture, we're going to pull this thing out, and this thing is going to sit there. Now, we are pulling on it, so there is going to be some tension in the line, wanting to keep it, but it's going to hold it and keep it from sliding. Okay, so that was, yeah, and that's why we can set the sum of the forces in the y are going to be 0, and the sum of the forces in the x are going to be 0. When we look at this, we've got the normal force, so I can go ahead and put that in. F1 is going to be this, minus t cosine 20. You can kind of look at this, but essentially from just this, without considering the bottom block at all just yet, we can come up with what the tension in this cable is, solving for that. And then what we will use on this one, we didn't need it to get the tension, but N1 will be something we will use when we get to the bottom block. That's coming here. This N1 is going to be related to this friction. There'll be mu sub s, or mu sub k, times this normal force will be that friction 1. And that friction 1 is going to be in the equal but opposite direction when we get to this one. Okay, as will this normal force here, call that N1, is the force of this bottom block pushing up on this block. Gravity wants to take it down. However, this normal force N1 also pushes down on the bottom block. Hopefully you can see why it's helpful to separate these two objects and look at the forces that are acting. These are all the forces that are acting from outside this object. So if you can isolate this alone, these are the only forces acting. Tension, mg, and then a normal force, and then a friction force. Okay, so get that. Okay, then we can focus on the bottom block. Okay, what are the forces acting on it? Wow, well, gravity is, M2G is pulling down. N1 was due to this guy. This block pushed up on this, action-reaction pushes down here. There's also this surface here gets another normal force. I call that N2 from this second surface. That's going to be up. Of course, this 100 Newton force, we're pulling at 10 degrees. But we're going to get two friction forces, one along the top surface with this block, which is going to be the same magnitude as that. And then F2, which is going to be along this bottom one, along this bottom surface. So we can take a look at that. Now from here we can look at the forces in the Y. I don't expect this thing to jump up or down. It's going to stay in the Y motion, but will be moving in the X. So in the sum of the forces in the Y, I expect to be equal to 0. So we look at all of those, the 100 Newton times the sine of 10 degrees. We've got a negative N1, we've got a plus N2, and then a minus M2G, the weight of this one. Now, common mistake here is, wow, don't we include, when we talk about the weight here, M2G, this guy's sitting on top of him. Should we include his weight?
No,
Why? Why not?
because it's included in like the normal force, right?
Okay, it's related, yeah, to the normal force. The idea that, in a sense, we are taking, N1 takes into account that this has some weight to it. Keep in mind, this weight was partially being held up by the tension in this cord. So really it was N1 here, and this one, that was handling the fact that gravity was pulling down, but the component of the tension was pulling up. And so the actual magnitude of N1 was less than mg of that point. Yeah, we're looking for some convenient numbers there. So in a sense, the weight of that one is taken into account here with N1. That's built into it, so we don't do it again by tacking on another weight of the top block. Subtle issues, but important. We're looking at just the forces that are coming in from the outside that are acting on this. Gravity is, for this object, is just acting on this one. And there's gravity on that one too, but the two are not tied together directly through gravity. They're through the surfaces. Okay, so again, some of the forces in the Y are going to be 0. Some of the forces, and I did this, my math, these guys caught me. There's a couple mistakes here. If you downloaded your solutions from before, I've got a little X here. I call this cosine 10 degrees. I was jumping in my mind down to the next line here, and it should have been the sine. I'm taking this over to this side of the equation. I think the numbers are okay. I just didn't copy it down right. Then we do that. We can take this. I already know what N1 is. I know this other stuff. Can stick in the numbers. I can also stick in the numbers here. But I can solve for N2 in this equation. That I don't know. And come up with N2 when I look at these components. You know all the numbers here. You can stick it in. It'll be 26 newtons would be N2. So we've got now the two normal forces, and so now we can look at the sum of the forces in the x direction on this. We've got that 100 Newton times the cosine 10 degrees pulling us in the plus direction. Minus, we've got the two friction terms are in the negative direction, so it's a minus mu sub k times N1, minus mu sub k times N2 for these two frictions. And let's see, I think that's all of it in the x direction. That should equal this one's mass times its acceleration. And so we do the numbers. I come up with an acceleration of 6.41 meters per second squared is what would take place. So go through the details on this. It's a good problem, and it really shows you the power of taking things apart piece by piece and looking at the free body diagrams for those. Yes?
So, this is a conceptual question. So, the 5 kilogram, that does not move. It's only the 10 that moves, right?
Correct.
So, it says the coefficient of the friction between the 5 and 10 is 0.2.
Oh, right.
So, does that mean the 5 kilogram is, so the friction between them is a static friction because the 5 is not moving? And, no?
Okay, but good question. Yeah, the 5 isn't moving, but the question is on those surfaces, they are slipping and sliding on one another. If those surfaces are pushed together and they're not budging, that's static friction. And so even though this block stays at rest, when we pull this other block, that surface is going to be moving. And so that would be kinetic friction. Okay?
Just another question. I noticed, so whenever there's a friction, does that mean we have to take the y, we have to solve for the forces in the y?
Generally, what you always want to do, it's going to be the coefficient of friction times the normal force. So you need to get the normal force, and that friction is always in one direction, the normal force is in the other direction. They're really like components of the force from the tabletop on this object. It's really the sum of those two is what it is. And we automatically, immediately break it down into the normal force is always going to be perpendicular to that surface, and the frictional force would always be parallel along that surface. So if we look at something, let's say, at an angle, and I think I've got some things coming up that will have that kind of situation. So, okay, yeah, lots of good questions. Was there any other that seemed like somebody wanted? Okay.
So, as a general strategy to solve these kind of problems, it seems like you're prioritizing finding n from the forces in the y direction first, and then plugging that into the
Okay, yeah, I think that certainly that's what I did here, and I think that would be fairly general. Now, a lot of times there's many ways of doing the problem, like the previous problem. We could have started on the other side and come back. Very often there's many ways of laying it out. Think of these problems as like a big jigsaw puzzle, where you're going to lay out your pieces and you're going to start to fit them together. And there's no one right way you have to do this, this, and this. You look at like Dr. Young, he's just laying the problems out just so clear, and people say, well, I would have never thought of that. You maybe think of something else. But so you start putting your pieces like a jigsaw puzzle, and you want to start to see what fits. And you might work a little on one problem and go over to the other side and start playing around, checking your pieces till you all can start to pull it all together. And there's not always a real simple strategy. But best thing, of course, here as far as the basics is drawing your free body diagram. I could have started on the bottom block. I probably would have come to something like this, where say, I don't know what, I can't get to the acceleration because I don't know N1. I need it. And then you might go up and come back here and find it and say, oh, I've got it now. Now I'll put it in. So you don't necessarily have to get that first, but you probably will need to get it at some point. So. Okay, how about another one that's kind of nasty, and this is for this is for you. We've got that 25 kilogram block, and this is kind of crudely drawn here, but there's going to be a hanging weight here. This cord is consider that this is going to be a ideal pulley, massless, frictionless. It's connected with some kind of bracket here to this block here. And so all of this is going to be kind of one thing. There's going to be a cord that's going to be tied, let's say, on the center of this thing along its axle. It's going to come out here. It's going to go around this pulley. This is a fixed pulley. It's not going to move. The cord then would wrap around that and come back over here, where it goes around yet another pulley and drops down to this mass. There again, this pulley doesn't move. It's fixed. So these are both fixed pulleys. This one will move with the block. So we need to be real careful on what we're going to be doing. We have a 25 kilogram rectangular block. It's connected to a 7 kilogram sphere through a pulley. If the surface, okay, there's frictionless, so that's That's kind of nice, or it's one less thing to deal with. Okay, what is the acceleration of the rectangular block? And assume the pulleys are frictionless and massless, and that the cable is massless as well. Okay, so it's just got those properties. Okay, so I decided to kind of redraw this, make it a little bit neater. Again, this is the block with the pulley attached. We're going to tie the string. It's going to go out here around this pulley, out, around, back over this one, and then it's going to start here. This mass, the 7 kilogram mass, is going to start to go down. As it goes down, it's going to start to pull on this cord, and is going to start to move this thing. Now, keeping our wits about it as far as what's happening. Let's start with this guy, since he's the most familiar. He's going to be hanging, let's see, I need to determine a direction I want to call positive. Well, I expect that this thing to go down, and that this thing will go this way. It's not likely to go the other direction. So I'll assume, and I didn't mark it here, but this is going to be the plus direction, as it would be in your standard case. In this direction, I've got it here, plus x2 is going to be down. So x1, let's say this one is going to move some distance, and this pulley thing I've got, this blue thing, represents this pulley when it gets over here. Of course, it's got the whole block with it, but I don't want to get too much clutter on here. So this pulley is going to get dragged over to here, and this will move through some distance, x1, and this one will come down. Now, don't assume that this thing is going to move the same amount. It's going to move, call it x2, and I expect that it's going to move through a greater distance than this one. Okay, here's how I would kind of reason that. Let's say we're going to start here, and we're going to move, and let's say finish over here. We're going to go through some distance. Now, this 7 kilogram mass is going to pull the cord straight, and we're going to pull it down. Now, when this thing ends up over here, this cord, and this cord will need to move through the pulley systems. They're through here, out to here, coming here, and we will need to take, if you imagine taking this amount of string here, or cord, this amount of cord, this amount of cord, we need to take that away. We need to remove 3x1 off of this side, get rid of it, so that all we end up with is a picture looking like this. And that will go over to the amount that this one is going to move. So I've got x2, the amount this one goes down is x1 plus another x1 plus another x1. That's these 3 cords, 1, 2, 3, that are going to get taken up. Okay? This is kind of tricky to see, although the math here is not real difficult. So we need to get that. Now, what will be important also is start with this idea, what I call the displacement. As this thing moves from start to finish, it undergoes a displacement of x1. And hopefully you see my argument that x2, the amount this moves, is going to be 3 times that. Again, since it's taking up this 3 sections of the cord. And so that in terms of displacement, I expect x2 to be equal to 3 times x1. And you see my use of the subscripts, the 1 for this guy and 2 for this one. So that's that. Now what is handy with this, we can take this and we can take the derivative with respect to time. If I take this expression, take the derivative with respect to time, then that's going to be v2, just dx2 dt, that's v2, is equal to 3 times dx1 dt, that's going to be v1. I can take one more time, take the derivative again, taking the derivative of velocity is the acceleration of 2. And I take the derivative of this, the 3 stays, and derivative of v1 dt is a1. So this relates the two accelerations. They're not the same. Acceleration 1 is going to be something, and that's what he's actually asking. He wants the acceleration of this one. But this one, since it moves 3 times as far, it's going to be moving 3 times as fast, and it's also going to accelerate at 3 times the amount of a1. So some of these can get rather tricky when we're dealing with these kind of pulley configurations, but this is how we want to start off with this. Okay, and then I can start to apply Newton's laws to these 2 separate bodies. Again, I'm calling this the plus direction, and then that would imply that this is plus going down, so I can tie these 2 together. I will need to do that through the tension. We'd start off with this block, doing that, the sum of the forces. Ooh, this is a tricky thing to see. Maybe let me do this one first. This is the easy one. You might look at that and say, whoa, what's going on? On this one, I'm calling down positive, so sum of the forces in the x. This goes in as a positive quantity. Tension is pulling back, minus t, and that should be equal to this one's mass, m2, times its acceleration, a2. And of course I can manipulate and get the tension, and I'm going to take it over to here, but I could, as you suggested, I could play over here and come back into this one. It doesn't really matter how you want to tie that together. Now let's come to this block. Okay, well, a couple of things are obvious. The m1g and the normal force is up. From this I could conclude some of the forces in the y, that the normal force is equal to m1g. It's true, but I'm not going to need it. I don't need it because there's no friction on this surface. If there was friction, I would need to get the normal force and use that to find the frictional force. And that's not a big extra thing to get, but we've got enough kind of on our plate right now. Take a look at this one. I've got this kind of an arrangement. The idea of Newton's laws, we deal with net forces. They're really the external forces. If you've got some object, you want to think of this thing, it's got a bunch of things internal. You've got all kinds of billions of atoms and things in there with forces between them. But the idea of all, we say internal forces, is that they're all part of action-reaction pairs, and they all cancel out. So when I say the net force on this thing, I don't need to worry about forces that are happening inside the material, since they would just cancel. I want to get all the forces that are coming in from the outside. So what you want to do when you apply this, you want to imagine encompassing this thing in kind of a little mathematical bubble around this thing and asking yourself, what's coming in from the outside? So I'm going to cut this thing across like this and separate this, or maybe I'll draw this. I'm going to cut through 3 chords. And each of those 3 chords has the tension that's in the system, or in the chord. So we really have 3 of those pulling in the x direction, and that's going to cause it to move. So we can look at that block. The sum of the forces in the x are going to be 3t, because this is not an obvious thing. It's got to be equal to this one's mass, m1 times a1. And you can kind of see that the math isn't really difficult. I solve this one for t and substitute it in here is the way I've done it. And we do a little bit of the math. That's pretty straightforward. And I come down to the acceleration a1 of this block. So that is a1. That's what he was asking for, the acceleration of the rectangular block. If you wanted to get the acceleration of this thing going down, well, it's going to be exactly 3 times that. Would be a2 if you wanted to get that. Okay, so there's kind of these 2 points of view that are worth repeating. The idea of when we get these multiple lines wrapped around the pulley, when there is a displacement this way, how much cord needs to get moved over to this side to make that happen. And it's 3 times whatever that one was. And that gets our basic relationship. That's the best way to start sorting this out. Taking the derivative, you can get the velocities. This week we're going to use in energy problems where we want to get the velocity of one compared to the velocity of the other. With forces, typically we want to get the accelerations related here so that we can do this. I did need to have A2 is 3 times A1 so that when I came back in here, I was able to replace A2 with 3 times A1. Because when I substitute back in, I've got an A1 here, and I wanted to solve for A1. So get a piece of scratch paper and do it for yourself. Again, there's no right way. You could have taken this one, solve for t, and come into here, and you can still do the problem. It's not a big deal. Yeah?
Can we say that because there's 3 different functions acting on the 25, so the last part where it said A2 equals to 3A1?
This one.
In the box on the right side. Yeah, that one. A2 equals to 3A1. Is that because 3 different tensions are acting?
Okay, in general, I would say you want to look at how these things get displaced. I'm going to have some more examples of things like this. I want to hesitate to be overly general. What I would say is get some, try to relate it to a displacement. So when this block does come from here over to here, it has undergone this displacement. And then it's not always easy to see these things. My argument is that we have to take up all the slack in this line as we go from here. Where have I got slack? I'm going to have stuff here, here, and here. I've got 3 of those, and that's really where this is coming in as far as getting at the velocities and the accelerations. Okay, tricky. Maybe as we do a couple more examples like that, you'll maybe start to see that. I wish I could give you just an easy prescription, and I don't think I have one. Each problem can be a little different, and some of them can be very tricky to see, as I'm sure you find this is tricky to see.
Well, you got the velocity by integrating the position?
Yeah, basically that. Just the position is just taking the derivative with respect to time. We can get to the velocities. These are we're going to want to use if this was an energy problem. You want to use velocities. In force problems, typically F equals ma, we're going to wanting to have accelerations.
But wouldn't you have just, you would have to square that and divide by 2 if you go from position to velocity?
Right. You'd probably want to go into kinetic energies, and then you'll be doing v squared. But this way, you'd kind of reason this first, and then take it into the problem. Okay. Again, I think I've got another one coming up. Yeah.
For the falling mass, you use f of the x. Isn't it moving in the y direction?
Oh, okay. If you want to call it y, I called it x. In a sense, this is x. It comes down to its label. If you want to call it y, that's okay. However, I would say that your best bet is to avoid sign problems. You don't have to. You could say, well, y is, I'm going to call that positive. This thing's moving this way. And then you'd have to say, well, your change in x here is equal to a minus change in y. You can do it, but generally I think it's best for most students that I've seen is if the thing is moving this way, that means this is going down. And so I called x2 positive coming down. Again, the x is just a label. If you want to use a y, you're welcome to it.
I understand why you did that, because the movement of the falling mass is a function of the movement of the top mass.
Yeah. Okay, and you'll notice in all of this stuff where I plugged in, I didn't actually use that x. You may find that with energy methods that you'll want to use the x, or x or y or whatever you're doing.
Okay, so again, like I'm kind of looking for generalities here, but if the movement of a second mass or object is kind of as a result of the movement of another, it's easier in terms of when you go for the final calculation to make the summation of those forces in terms of the first one.
Right, I believe you've said that correctly, yeah. Okay. Okay, so, well, hang on to some of those ideas. Again, I'm going to kind of come back to some other examples similar to this, but I think, okay, let's see. I was going to do some stuff with circular motion. This is kind of, this is a good breaking. Let's have a little, something that's a little simpler, and then we can take a break. Okay, how about circular motion? I'm kind of breaking this up. The last stuff was chapter 5, really, where we get introduced to forces. And now it's got some topics in chapter 6, which are kind of little add-ons to this. It falls within Newton's laws. The idea of something traveling in a circle. Usually, kind of the simplest example is a ball and string. Now, what can be helpful with a ball and string, your intuition very often gets in the way, because you'll swing something around and you can say, wow, I can feel this outward pull. I can feel it, and you can. Your senses aren't deceiving you. But the idea that like the tension in this cord is pulling in on the ball, the tension on the cord is pulling out on me. Now, we want to look at the forces that are acting on the ball, not the forces that are acting on me. I'm feeling and describing the reaction force. We want to focus on the action force, and that's always going to be directed into the center of the curve. Just like when we dealt with centripetal acceleration, or if they call it radial acceleration, regardless what you call it, it's directed into the center. So the idea is, suppose we've got like a hockey puck on a string swinging around in a circle, and just hanging a mass on that. Here we've got the tension. We could have this thing moving as well. I'm just consider this thing kind of in equilibrium, where this tension is being held here as this thing goes around. And what do we have? Mass M1 is being held at the same height. Okay, so it's not going up or down. And what is the tangential speed of M1? So it's going around. So this is just kind of a simple example. The hanging mass, we've got, it's going to be set equal to 0. It doesn't really matter whether you want to call up, down, or positive, but I've got up T minus M2G, and so this tension is just equal to the weight of this thing. That makes sense. But that tension is going to be applied to this thing, and it's pulling into the center of the circle here. So on the disk, the sum of the forces is going to be m1 times the acceleration. Now, here's where we want to think about either centripetal or radial acceleration. We kind of use those almost independent, but that centripetal or radial should be v squared over r. So we know the acceleration has to be that if it's going to be traveling in a circle. That tension gets applied to that, so I take this tension back into here. Again, I'm tying these two things together, although this is simpler. And then we can solve for the tangential velocity by moving this over to the other side. And I got the square. I can take the square root of it. I think the math is simple enough. You can read this. I'm just kind of using this as kind of an intro to the idea of circular motion. We're going around in a circle. If we have something where, called conical pendulum, this is a pendulum. It's not like an ordinary pendulum, that swings back and forth like this. The conical pendulum gets set, and it stays at the same altitude if you got it set right, and it's going to go around in a circle. So the idea that if we're going to apply forces on this thing, like the tension in the cord, this thing is going to go around. It's not going to go up or down in the y direction, but it is going around in the centripetal or circular direction. So what do we got here? We've got, we've got a 1 meter long string set in a horizontal circular motion. If the string makes an angle of 30 degrees, what is the period t of the pendulum? Actually, I should be tau. I ended up changing. I had a T for tension here, and then I had a T for period. And I changed that to a tau this morning, so so it's not so confusing. But let's go back to the tensions here. Some of the forces in the y direction, we've got T times the cosine of theta. So if you've got theta here, theta is here. Oh, I guess we got this here is that. So we've got T times the cosine of theta is the vertical component. That should match with minus mg pulling down. That should be equal to 0 because it's not going up or down in the y direction. Some of the forces in the radial or the centripetal direction is going to be, let's see, this picture's here, so the center of the curve is over here, back in this direction, and so that's going to be T times the sine of theta. That should be equal to ma. For circular motion, that was v squared over r for the acceleration. Got that. He didn't tell us the mass of the ball, but we could cancel that, and then we can certainly get the speed that the thing is going around. Now you want to watch this. Small r is the radius of this circle as it goes around. And we also have that this was given as 30 degrees and the length was 1 meter. We can solve for that radius, L sine theta, that should be obvious. And then that should come into here. We can get an expression for the velocity. Okay, I didn't, I'll stick in some numbers here, and I did that wrong here too, so we got that. So I've got the velocity. Now as far as getting the period, think in terms of the distance is equal to velocity times time. It's going to be going at a constant speed, or maybe I should have said distance is speed times time, just simplify that. The distance around is going to be one complete rotation around, a revolution, is 2 pi r, and that should be the velocity v times the time, and that would be the time of the period to make one revolution. So I think this is kind of the easiest way to think of that. And so that period is going to be equal to 2 pi r over v, just solving for that. And we can go ahead and stick in the numbers here. And I stuck in the numbers too and did it wrong. I was having I had this tangent, and I was calling the root 3. It's not. It's 1 over root 3. I messed up, so I put that here. So the corrected here, it should be 1.87. So if you got that first batch, you might want to either download it again or just take mental note of where I screwed up. Okay, so I intend this to be kind of a simple, relatively simple example, but kind of bring us into circular motion. Let's do a couple of these examples. Might be good as far as then taking a break after this. Okay, we've got a roadway here that's kind of up and down, and we have a car drives over the crest of a hill traveling at a speed v such that the car just starts to fly off the roadway through the air. Have you experienced this? You're coming up over the top of the hill, you're traveling fast enough. If you're traveling fast enough, you can actually leave the surface here and go flying off on a parabola, it's like a projectile. If you lose contact, now by losing contact means your wheels start to come off the ground. So what about the normal force? If I look at the forces that are acting on this thing up at the top, we've got mg down, and we've got the normal force from this surface is up. And if we're going to start to lose contact, the wheels are starting to come off. They're not touching anymore. So what about the normal force? 0. Has to go to 0. So at the top of the hill, the loss of contact n approaches 0. The normal force does, and so I can look at these forces. I'll put it in there as though it's of consequence. It's going to be mg. I'm calling into the center of the curve positive. I think that's the clearest way to stay out of trouble. So it's plus in this direction. So mg goes in as a plus. The normal force, if it's up there, is going to go as a minus. That's the net force, and that should equal ma. The a is v squared over r. And we can use that to solve for the velocity that you would be traveling. Okay, and then if the car maintains the same speed at the bottom of the hill, what is their apparent weight now? Okay, in fact, this was here. If you were sitting on the seat here in a car, the normal force, not only on the car, but the normal force on you would tend to go to 0. And that's where you're going to feel, particularly in the pit of your stomach, where you start to come off the roadway, in a sense, where you're going to feel that. You're going to feel weightless, is how it often gets described. Normal force is 0. The passenger's apparent weight is 0 up on top. Think about if you were in there and you're sitting on that bathroom scale, and go back to that idea of the accelerating elevator car. This is actually a car that's going down and dropping. Okay, anyway, enough talk. Okay, if the car maintains the same speed at the bottom of the hill, what is their apparent weight now? We have 2 of these radii there are the same. So at the bottom, we want to draw the same kind of force diagram, but you want to consider that the circular path that it's taking at this point is this is the center of the curve. So we want to call into the center positive, away from the center negative. So the order of these things get reversed here. This goes in as a plus minus mg. That's equal to mv squared over r. From the top one, we got the velocity that we were flying off this curve at the top. We bring that same velocity into this case and solve for the normal force. And that's going to end up being, when we get this, do the math here, it's going to be 2 mg. So the apparent weight, that is the normal force, or if they were sitting on a scale, that normal force would be this 2 mg. And so the passengers will end up feeling twice as heavy, or we say they experience 2 g's of force at that bottom of that curve. Okay. Okay, so a couple other circular things. This is fairly simple as well, just a curved road. Let's say you've got like a driveway or something that's a big circular loop, and you're going to, let's say, drive on this thing and maybe pick up speed. And you want to be able to make the curve, and after a little, you keep going faster and faster, all of a sudden you start to hear the tires are starting to squeal. That means these surfaces, you're starting to go into a skid, and those surfaces are going to be rubbing on one another. Now, what we'll do for this car as it goes around, to keep it, we've got really 3 forces, and we're looking at it from the side here. Of course, gravity pulls down. The normal force is up. The force of the friction, we need the friction of the tires on the road in order to provide a force that's off this way or directed into the center, very center of the curve, would be that friction. And it would be static friction, because these tires are going to roll on one another, and as long as they're rolling, these surfaces aren't skidding. Once they start to skid, typically then this becomes, instead of static friction, the kinetic friction, which is less than static friction. And so usually when it starts to go into a skid, you're going to lose it and you're going to fly off the roadway. Newton's first law, it wants to travel in a straight line. And so the idea is, if you maybe have icy conditions or you lose your friction, you're just going to fly off on a straight line and off the road. So the idea that if you want to have some maximum speed, you want to be up to maybe the maximum of static friction, let's say. So F sub s is at its max. It's going to be up to mv squared over r, where that v would be the maximum speed, where it could still go around the curve and not wipe out. With mu sub s going for the friction, the m's drop out, and so this would be the expression we could write for the maximum speed that we could go around this flat curved road. Now, do this to kind of segue into like the banked highway problem. The idea we need friction here. If it's icy conditions, we don't have that friction. Again, we just go flying off on a straight line. So a way around this is to build a banked highway. The picture of this is that there's this is kind of the center of the curve. And if we look down on it, it's a big curved section of roadway. The vehicle is going to be driving around this in kind of on a conic shape here as it goes in. And right here we're drawing it with this thing going straight into the board. We got a little bigger picture here where the car's going in. The roadway is such, and it's banked at some angle. And the idea is you could bank this at some angle such that if the car is traveling just the right speed, it has to be designed for a particular speed, you can go around this curve and make the curve with not requiring any friction at all. All we use is the force of gravity and this normal force, which when we tip the roadway gets tipped in towards, and we'll have a component into the center of that curve. Okay, so we can take a look at probably the first place to start is we want to be able to go around this curve, and we want to have it designed. Let's just look at the picture here, or the description. The Caltrans wishes to build a banked highway on a new freeway exchange. The radius of curvature needs to be 200 meters. At what incline angle should the road be built for safe travel, designed for 55 miles per hour? Okay, safe travel being defined as zero friction traction needed at that speed. And he gives you the conversion here, so you'd have to convert miles per hour. And I do 55. I do a little conversion here. You know how to do this stuff. Turn it into meters per second would be the speed that I'm going to use. So that's how fast we would be designing this for. So in the y direction, we want to set the sum of the forces in the y to be equal to 0. The idea is that very often, we have been taking this, we've been tipping our axes like this. You can do it this way, but I'm going to follow what the book does, where they make this the x-axis, this the y-axis. The idea is if you're going around this bank here and you don't leave your lane, you stay in your lane, you shouldn't be going out of your lane going up or sliding this way going down. You should be at the same level. And so the idea is some of the forces in the y should be 0. So we've got the normal force times the cosine of theta, that's up, minus mg, the weight of this thing, just two forces, that's it, is equal to the normal force mg over the cosine theta. Then we look at the radial direction. This is what I need. I need to have acceleration into the center so I can make that curve. Some of the forces in the radial direction, I really only have one. I've got the normal force as an n sub x, or I would call it n sub y, or r, coming into the center. And that should be n times the sine of theta. And that should be equal to ma, or mv squared over r. From the y motion, I can get the normal force to substitute it in. When I have that, I get the sine theta over the cosine. That's the tangent of theta. So we get mg tangent of theta is equal to mv squared over r. And something that's curious here is the m's cancel, which is really nice. This is nice because then this design works for small vehicles like motorcycles, cars, trucks, semis. It wouldn't matter on the mass of that would drop out, and we just are left with the tangent of that angle is equal to v squared over gr. So now we're prepared to calculate this for that particular speed, 55 miles per hour, in a 200 meter radius of that curvature. We can get the tangent of this, and in turn get the angle, 17.1 degrees. and that's the angle we would bank. Okay. Now again, this is strictly for your vehicle traveling precisely at 55. There's no need for friction, so you can have icy conditions. You should be able to stay in your lane and be able to make the curve. You have a homework problem that plays on this one more step. They say, well, what are the range of speeds? The idea is if you're traveling faster than that 55 miles per hour, you never do you? As you come around here, there's a tendency you would tend to slide out of your lane because unless you've got friction. So if you're traveling too fast, you also need a component of friction down the incline this direction. And then that would be for some maximum speed, such that that friction wouldn't quite let go. And then if you're traveling too slow, there would be a tendency, if these were icy, you just slide down the road. You need friction back in this direction to keep you in your lane. So you only need friction is if you're varying your speed from that ideal 55 miles per hour. The homework problem, it'd be well worth taking a look at it. It's a little involved. I don't want to take the time to do that, but I'll mention that as kind of an add-on to this. Okay. Oh, okay, let's see. Do you want to take a break now? Maybe this would be a good time. You're going to talk about resistive forces. This is kind of the hairy stuff, or a bit of hairy stuff. And then we'll get into, I believe, energy right after that. So why don't we take a 10-15 minute break and come back. Wait a second, what time? Is this the right time or is this? Okay. Well.
Yeah, I was like going around.